Good morning, students. You are all welcome to session 1 of vector spaces classes. So, you have studied groups and rings and extension fields or fields in your first semester classes. Okay. So, group is an algebraic structure with a single binary operation, and ring is an algebraic structure with two fixed binary operations. One is the addition and the other is multiplication. Okay. Now, we are going to study another important part of the algebra, which is the vector spaces. In this semester, we will study both vector spaces and linear transformations. There are two important chapters, vector spaces and linear transformations. Okay. So, I refer again the topics in algebra by I.N. Arnstein for the reference, and also supplementarily I will take up modern algebra by Surjit Singh and Quasi Zamiruddin, and university algebra by Gopalakrishna, and linear algebra by David C. Lay and many others. There are wonderful textbooks on vector space, this one linear algebra. You can refer any of the text that is available in the internet as well as in the library. So now if we come to vector spaces, so one thing that you already familiar with, okay, the motivating factor for groups theory is the set of all one-to-one mappings from a set onto itself, that is permutations. Similarly, the motivation for rings is the set of integers. So the third algebraic model that we are going to study is the vector space, which originates from the notion of a vector that you already familiar with in mechanics or in geometry. Here we are not going to study the geometrical view of a vector. Instead, we are going to see the vector as in the algebraic view. So more generally, we treat the vector as the pair A comma B, the pair ordered pair A comma B. So where AB is the we consider AB as the terminal point relative to terminal point of a directed line segment relative to some fixed coordinate system. Okay. So the formal definition of this one vector space will be defined like this. Okay. Suppose V is any non-empty set. V is said to be a vector space. V is said to be a vector space over a field F, vector space over a field F, if V is an abelian group under addition. The first condition is V should be an abelian group. Abelian group. And for every alpha belongs to F, and the element V belongs to V, we have the element alpha into V must belongs to V. Alpha into V must belongs to V, subjected to the following conditions. What are the conditions? The conditions are alpha into, say, V1 plus V2 is equal to alpha V1 plus alpha V2. Second is, say, alpha plus beta into V1 is equal to alpha into V1 plus beta into V2, right? The third condition is alpha into beta times V is equal to alpha into beta times V is equal to, say, this is alpha beta into V. Fourth one is 1 into V is equal to V for every, these are the elements, for every V belongs to V, for every V belongs to V. So this property here 1 represents the unity element of F, under multiplication. Here the members of F are called the scalars and the members of V are called the vector space. This property is known as the vector addition, and this property is known as the scalar multiplication. Vector addition, scalar multiplication are the operations here. So we denote the vector space V over F by V of F or VF, okay, or simply you know that the field F is always some fixed field, so V is equal to simply vector space by V. Okay, so now let's look at the few examples. Example 1. So suppose F is any subfield of the field K. Suppose F is any subfield of the field K, then K may be regarded as a vector space over F. If F is any subfield of K, then K may be treated as K is a vector space. K is a vector space over F. K is a vector space over F. K is a vector space over F. Say for example, say you know that R is a field. So I can take R over R. F is R, V is R. R over R is a vector space. C over R. Set C denotes the set of complex number. C over R. Again C over C. Set of complex over the complexes. Okay, they are all vector spaces. Now the question is, can R over C means F is C, V is R, is a vector space, but this is not a vector space because R is not closed under scalar multiplication, because if you take V is R, F is C means I will take alpha is equal to say some 2 times I. Okay, and the vector V is equal to, set it is real number, say 4. Then according to our condition, scalar multiplication, alpha into V must be element of V, means it must be element of R. But alpha into V is what? 8 into I. 8 into I does not belongs to R. So the basic property itself fails here. Therefore R over C is not a vector space. Okay. So R over R is a vector space, C over R is a vector space, C over C is a vector space, but R over C is not a vector space. Let's take the next example. Say suppose here hundreds of examples we can construct of a vector space. So F, I will take F be any field. F be any field. Say if F is any field, let V be the set of all n tuples of elements of F. V is the set of all n tuples of elements of, say this is x1, x2 and so on xn, where each xi is an element of F. I will take V is the set of all ordered n tuple of elements of F. Definitely this is a vector space over F. This is a vector space over F, because what are the binary operations here? You take say x comma, say x and y are any 2 elements of V, means x is a n tuple, say x1, x2, etc. xn is one element, and y is what? y1, y2, etc. yn. Where this xi lies? Xi lies in, say xi lies in F, and yi also lies in F. So then x plus y, I will define an operation addition as x plus y is what? x1 plus y1, x2 plus y2 and so on, xn plus yn. Okay, and the scalar multiplication will be defined as alpha into x is equal to alpha into, say x is x1, x2 and so on xn. So this is equal to alpha x1, alpha x2, etc. alpha xn. Definitely this is an element of both x plus y and alpha into x are elements of V only, because they are n tuples of elements of F. Because if x1 belongs to F, alpha into x1 also belongs to F, and x1 and y1 belongs to F means x1 plus y1 belongs to F. They are elements of n tuples of elements of F only. Therefore they are the therefore we can declare that V, if F is any field, V containing the set of all n tuple of elements of F is also vector space. So instead of F, I can take F is equal to say R, if F is the field R, then what will happen? Rn, you know that Rn is a vector space over R. Rn is a vector space over R. Cn is a vector space over C. Okay, Rn, you know that it is a vector space over R. Okay, next, say if you want to discuss another example, say again I will take FB field, and V is, this is little interesting. So V is f of x. You know what is f of x from the field theory. So you know that V is f of x means it is the set of all polynomials in x over f, right? V is set of all polynomials. Okay, say this look like say C0 plus C1x and so on, Cn x power of n and so on. They are infinite sequences where each Ci belongs to f, because it is V is the set of all polynomials over f. Then definitely with respect to the addition of polynomials and with respect to the multiplication of a polynomial by a scalar, V is a vector space over f. Okay, V is a vector space over f. Next one is, so I will take V to be for example 4. Say I will take V to be, say m set of all m cross n matrices, m cross n. Say this is set of all m cross n matrices over the f, over the field f. F may be a real or complex. Then with respect to the addition of matrices and the multiplication of a matrix by a scalar, so V forms a vector space. V forms a vector space. Next is you can take V to be a set of all, V is the set of all real valued continuous functions defined on the interval AB. This example, this type of example we have considered in ring theory. While proving as maximal ideals, we have taken such example. V is set of all f such that f is f from AB to R is continuous. Continuous means V is the set of all real valued functions. V is the set of all functions, real valued functions defined on the closed interval AB is continuous. This is a set. Then we can show that this is a vector space. This is a vector space over R. Over R. So the binary operations is, so the sum of functions f plus g of x is what? So f of x plus g of x, and the scalar multiplication operation is alpha into f of x is equal to alpha times f of x. Definitely both are, so sum of any two continuous functions is continuous, and scalar multiplication of a continuous function is also continuous, means f is continuous, alpha into f is continuous, and f and g are continuous, means f plus g is continuous. Okay, these are the few examples that we have discussed. Next, let us take what are the subspaces. Subspace of a vector space. Subspace of a vector space. So suppose V is any vector space over a field f, and W is any subset of V. W is any subset of V. Then W is said to be vector space over a field f if W itself is a vector space under the operations of V. If W itself forms a vector space under the operations of V, then we say W is a vector space. But you know from your linear algebra that you have studied in your BSc classes itself, so W is any subset is a subspace if it is closed under addition and scalar multiplication. One is one condition, and also you know that say W is a subspace of a vector space V if for every pair of elements x1 comma x2 belongs to W and alpha comma beta belongs to F. So the linear combination alpha into x1 plus beta into x2, if this belongs to W, then we say W is a subspace of V. This is the condition that we use to prove any non-empty subset is a subspace. So what are the examples for a subspace? Examples are, so clearly if W is equal to 0, if we take only the set containing 0 element, as well as W is equal to, if we take W is equal to V, the whole vector space itself, then they are subspace, always subspaces of V. They are called the trivial subspaces. Okay. So example, if I take the non-trivial example, say you know that V is equal to R2 over R. Suppose V is equal to R2 over R, I'll take. Then I'll consider the subspace as W is equal to R2 over R, means how it looks, set of all pairs A comma B. So A and B are what? They are all real numbers. R2 over R means it contains pair of elements A comma B, where A and B are elements of R. W1 is set of all pairs, say A comma 0, where A belongs to R, and W2 is equal to say 0 comma B, where B belongs to R. Then definitely W1 and W2 are subsets of V. Can they are the subspaces? Yes, they are the subspaces. If you want to show, say let X comma Y belongs to W1 and alpha comma beta be scalars. Alpha comma beta be scalars. Here scalars means they are the elements of R. F means here R. Okay. Now X comma Y belongs to W1 means how X looks. X is look like say A1 comma 0, and Y, how Y looks, Y is equal to some A2 comma 0, where A1 A2 are elements of where A1 and A2 are elements of R. A1 and A2 are elements of R, and alpha comma beta be this one real numbers. Then alpha into say X plus beta into Y. Alpha into X plus beta into Y is equal to what? So alpha into X means A1 comma 0 plus beta into A2 comma 0. This is equal to what? Alpha A1 plus beta into A2 comma 0. Where this lies? This definitely lies in W1 itself, because for A1 A2 belongs to R, then since R is itself is a vector space over R, alpha A1 plus beta into A2 belongs to R, means this is an element of R comma 0, means this is an element of W1. Therefore, for the elements X comma Y belongs to W1, alpha X plus beta Y belongs to W1, therefore W1 is a subspace of V, means V is here R2. Okay. Similarly, we can show that W2 is also a subspace of R2. Okay. So next is algebra of subspaces. Algebra of subspaces. Algebra of subspaces means here we discuss the union of top subspaces, the sum of any two subspaces, and intersection of a subspaces likewise. Suppose we have W1 and W2 are any two subspaces of a vector space V. Then their sum W1 plus W2 is defined as, W1 plus W2 is defined as what? So this is X plus Y, where X is an element of W1 and Y is an element of what? W2. So W1 plus W2 contains set of all elements of the form X plus Y, where X is first one is an element of W1, second element is an element of W2. Clearly, so W1 plus W2 is also a subspace of V. If W1 and W2 are subspaces of V, we can easily show that W1 plus W2 is also a subspace of V. So this definition can be extended to any number of subspaces. That to say, if W1, W2, etc. Wn are subspaces of a vector space V, then W1 plus W2, etc. Wn are all is also a subspace of V. Next is, so suppose W1 and W2 are subspaces of V. How do you define W1 union W2? How do you define W1 union W2? This is contains set of all elements of V such that they should be the elements of V such that X belongs to W1 or X belongs to W2. Because it's the union, they are in either in W1 or in W2, then definitely they are in the union. And W1 intersection W2 is equal to what? W1 intersection W2 is equal to set of all, again X belongs to V, such that X belongs to W1. Here the compulsion is, so X must also belongs to W2. Means W1 intersection W contains those vectors in V which are in W1 as well as in W2. We can clearly show that W1 intersection W2 is a subspace of V. W1 intersection W2 is a subspace of V. If you want to show this, say you take any two elements, say again, let X comma Y belongs to W1 intersection W2 and alpha comma beta be scalars or in the elements of F. If X comma Y belongs to W1 intersection W2 means X and Y belongs to W1 as well as and X comma Y belongs to W2. They are both in W1 as well as W2. Now W1 is a subspace and XY belongs to W1 and alpha comma beta are scalars. Therefore, by definition of a subspace, alpha X plus beta Y belongs to W1. Similarly, as W2 is also a subspace, so alpha X plus beta Y also belongs to W2. Therefore, alpha X plus beta Y is in W1 as well as in W2. Therefore, we can declare that alpha X plus beta Y belongs to W1 intersection W2. So, if alpha X plus beta Y is in W1 intersection W2, then you can easily declare that W1 intersection W2 is again a subspace of V. Okay. Now, the question is whether W1 union W2, whether W1 union W2 is a subspace. W1 union W2 is a subspace of vector space V. The answer is no, because look here, if I will prove this by taking in the general example. Say V is, I will take R2 as we discussed in the earlier example. V is R2 and W1 is the subspace. We have taken A0 where A belongs to R and W2 is what? Say 0B where B belongs to R. These are the two subspaces we have taken, right? Now, what is W1 union W2? W1 union W2, okay, let's W1 union W2 contains either of the elements of the type A0 or 0B. So now definitely according to our construction of a W1, so definitely 1 0 belongs to W1. Is it true? Yes. 1 0 definitely belongs to A is 1 here, and say 0 2 belongs to W2. Here B is equal to 2. Now, if W1 union W2 is a subspace, then it must closed under vector addition. Closed under vector addition means sum of any two elements of W1 union W2 must also be the element of W1 union W2, because 1 0 as well as 0 2 they are element of what? W1 union W2. Let us make a sum of these, say 1 0 plus 0 2. What 1 0 plus 0 2? This is 1 2. Now 1 2 is not of element of type W1 and also it is not type of element of W2. Therefore, 1 2 doesn't belongs to W1 union W2. Therefore, W1 union W2 is not closed under vector addition. Therefore, we can declare that W1 union W2 is not a subspace of V. So, the question is when do they are when W1 union W2 is a subspace of V. W1 union W2 is a subspace of V if and only if either W1 is contained in W2 or W2 is contained in W1. Say either W1 union W2 is a subspace if and only if what? W1 is contained in W2 or W2 is contained in W1. Okay. So, because see here, suppose W1 is contained in W2. W1 is contained in W2 means what will happen? W1 is contained in W2 imply W1 union W2 is equal to what? W union W2 is equal to W2. W1 and W2 is equal to W2. Since W2 is a subspace, W1 union W2 is a subspace. Again, if W2 is contained in W1, if W2 is contained in W1, then W1 union W2 is equal to what? It is W1. Since W1 is a subspace, W1 union W2 is also a subspace. Therefore, W1 union W2 is a subspace if and only if one is contained in the other. Either W1 is contained in W2 or W2 is contained in W1. Next definition. Suppose V is the vector space and W1, W2, etc. Wn are all subspaces of the vector space V. Suppose V is the W1, W2, etc. Wn are the subspaces of the vector space V. Okay. Then we say V is the direct sum of its subspaces W1, W2, etc. Wn. Direct sum of V is the direct sum of its subspaces. If every element of V can be uniquely expressible, every element of V can be uniquely expressible as x is equal to, say every element x in V can be expressed as, say, W1 plus W2, etc. Wn, where each Wi belongs to W. We say V is the direct sum of the subspaces W1, W2, etc. Wn if every vector x belongs to V can be written as sum of W1, W2, etc. Wn, and this expression is unique. In this case, we write V as say W1, this is called circle, plus W1, W2, and so on Wn. So we say V is the direct sum of this if V is equal to W1 plus W2, etc. up to Wn. And already you know from your previous discussions or previous semester, in previous classes you have studied that V is the direct sum of W1 plus W2. V is the direct sum of W1 plus W2 if and only if you have studied this. V is the sum of W1, V is the sum of W1 plus W2, and W1 intersection W2 is equal to, W1 intersection W2 is equal to 0. If V is the direct sum of W1 and W2 if and only if V is the sum of W1 and W2 and W1 intersection W2 is equal to 0, right? Now let us discuss one example. Say suppose V is the vector space of all functions from R into R. V is equal to, V is the vector space of all functions from say R into R. Vector space of all functions from R into R means real valued functions. Say, and I will take VE. I will take VE as set of all f belongs to V such that f is even. When f is a even function, V contains set of all even functions. V naught contains set of all f belongs to V such that f is odd. F is odd and even functions. So V contains set of all f belongs to V such that f is even. V naught contains set of all f belongs to V such that f is odd. You know, when we say odd, what is meant by an odd and even function? If f of x is equal to, f of minus x is equal to f of x, then we say the function is even. If f of minus x is equal to minus of f of x, then we say f is an odd functions. So now V is a set of all functions from R into R. V and I constructed, I taken like this, and V naught I taken like this. Then V and V naught are subspaces of V. V and V naught are subspaces of V. Moreover, V is the direct sum of V plus V naught. V plus V naught. So VE and V naught are subspaces of V, as well as V is the direct sum of VE and V naught. Okay, let's prove this now. Say now VE is a subspace of V. Say I will show VE is a subspace of V. So V is a subspace of V. So now can V can be empty? No, V cannot be empty because we have a function 0 function. 0 of x is, what is the function of nature of 0 function? 0 of x is 0, but this 0 function of minus x is also 0. Therefore 0 of x is equal to 0 of minus x. Therefore this is 0 function is a even function. So 0 function definitely belongs to V, and V cannot be equal to empty. So now I am going to show V is a subspace of V. For this I will take any two functions, say f and g belongs to V. F and g are even functions, and say alpha comma beta belongs to f. Alpha comma beta belongs to f, means f and g belongs to V, and alpha comma beta belongs to f. So now we need to consider alpha f plus beta g. What will happen? Let's see. Alpha f beta g of minus x. Alpha into f plus beta g of minus x is, so you know that this is alpha f of minus x plus beta g of minus x. Okay. So this is equal to say alpha into f of minus x plus beta into g of minus x. So this is alpha into, since f is an even function, so what will happen? F of minus x is f of x, and similarly since g is an even function, so g of minus x is g of x. Therefore this is equal to alpha f plus beta g of x, means alpha f plus beta g of minus x is same as alpha f plus beta g of x. This holds for every x. Therefore what you can say? Alpha f plus beta g is an even function, means alpha f plus beta g. So alpha f plus beta g belongs to VE. For f comma g belongs to VE, thus alpha f plus beta g belongs to VE. Therefore you can declare that V is a subspace of V. Similarly we can show that V naught is also a subspace. V naught is also, means V naught means set of odd functions. V naught is also a subspace. Now V is a subspace, V naught is a subspace, and sum of any two subspaces is again a subspace. Therefore V naught plus VE is a subspace of V. V naught plus V is a subspace of V, and that is V naught plus VE is contained in V. Okay. So you call this, say, by the equation, say 1. You call this by the equation 1. Now let f belongs to V be any element. Let f belongs to V be any element. Let f belongs to V be any element. Now you consider G be a function from R to R. G be a function from R to R such that g of x is f of minus x. Such functions definitely exist. So you define a function g from R to R such that g of x is equal to f of minus x. Definitely, since f belongs to V, therefore g also belongs to V. So such a function definitely exists in V. Now f can be written as, can I write f as half times f plus half times g plus half times f minus half times 1 by 2 times g. So f can be written as 1 by 2 times f plus 1 by 2 times g plus 1 by 2 times f minus 1 by 2 times g. Definitely if you add this you get only f. Okay. Now 1 by 2 times f plus 1 by 2 times g. 1 by 2 1 by 2 times f plus 1 by 2 times g of minus x. This is equal to 1 by 2 times of f of minus x plus 1 by 2 times of g of minus x. So this is equal to 1 by 2 times of f of minus x plus 1 by 2 times of g of minus x. So this is equal to 1 by 2 times of. So f of minus x is what? F of minus x is g of x plus 1 by 2 times of g of minus x is what? So if you put g of minus x is f of minus x, so this becomes f of x. F of x. So this can be written as of into f plus of into g of x. Means of times into f plus of times into g of minus x is 1 by 2 times f plus 1 by 2 times g. Means what we can say, this first term is an even function. Means first term belongs to where? VE. Similarly, we can show that the second term belongs to VO. Means the it is the odd function, set of odd functions. Therefore, every element f belongs to V can be written as a sum of an element of VE plus sum of an element of V naught. Therefore, what you can say, V is the subset of VE plus V naught. Already we have shown VE plus V naught, the sum is contained in V plus V naught is contained in V. Now we are showing that V is contained in VE plus V naught. Therefore, you can say that V is the direct sum of, V is the sum of VE plus V naught. V is the sum of VE plus V naught. Now, can this sum is a direct sum? To show this is a direct sum, what we have to show? Whether VE intersection V naught is equal to 0 or not. Let's verify this. Okay, understand now? So our aim is to show V is the direct sum of VE and V naught. So suppose you consider any two functions, say f belongs to VE intersection V naught. Then what will happen? F belongs to VE and f belongs to V naught. Both f belongs to VE as well as f belongs to V naught. Now f belongs to VE implies what? F of minus x is equal to f of x, and f belongs to V naught means f of minus x is minus f of x. F of minus x is minus f of x. Therefore, f of x is equal to f of minus x is what? Minus f of x. So f of x is minus f of x. So this implies f of x plus f of x is equal to 0. But 0 can be written as 0 of x, because 0 of x is 0 for every x, because 0 is a 0 function. Okay, so that function I may written by bold letter, say 0 of x. Okay, so this implies 2 times f of x is 0 of x. This holds for every vector x belongs to V. Now 2 times of f of x is equal to 0 of x implies f of x itself is 2 cannot be 0. So f of x itself is 0 of x, means f is a, this holds for every x belongs to x implies what? F itself is a 0 function. F is a 0 function. 0 function. 0 function. 0 function. Therefore, what you can say? VE intersection V naught contains 0. So we have shown V is the sum of V plus V naught, and we have shown V intersection V naught is equal to 0. Therefore, we can declare that V is the direct sum of VE plus V naught. Okay. So if V is the set of functions from R into R, and if V and V naught denotes the set of even and odd functions respectively, then V is the sum of V plus V naught. Okay. Okay, next let us discuss another definition. So suppose W is a subspace of a vector space V. W is a subspace of a vector space V. Then you know how to define the set V by W. V by W is contains set of all elements of the form X plus W, where X is an element of V. So V by W denotes the set containing set of all elements of the form X plus W, where X belongs to V. Definitely this is a subset of V itself. Definitely this is because X belongs to V, W is already is in V, therefore X plus W is an element of V. Therefore this set V by W is a subset of V. Can V by W is a subspace? Yes, definitely V by W is a subspace of V under the operation say X plus W plus Y plus W is X plus Y plus W, where X and Y are elements of V. Therefore X plus W, Y plus W are elements of V by W. The sum of any two elements of V by W, say I will define the operation like this: X plus Y plus W, and the scalar multiplication is alpha into X plus W is, so alpha X plus W. Now X belongs to V means alpha into X belongs to V, means alpha X is an element of V, plus W means this is definitely an element of V by W, and the first one is also an element of V by W. So with respect to these two operations, V by W forms a vector space called the, yes, you have studied this, quotient space. Quotient space. So in groups, we have constructed the quotient groups using normal subgroups, and here we constructed the, and in ring theory we constructed the quotient rings using S ideals, and here we constructed the quotient spaces using the subspaces, okay, using the subspaces. Now say suppose another definition I will define now. Say this is that, suppose we have two vector spaces. Suppose we have vector space V over F and another vector space say W over F. Suppose we have two vector spaces V and W. Say map T from V to W. A mapping T from V to W is said to be a homomorphism. Is said to be a homomorphism. Is said to be a homomorphism if, what is the condition? T of X plus Y is equal to, T of X plus Y is equal to T of X plus T of Y, and T of alpha X is equal to, T of alpha X is equal to alpha times T of alpha X is equal to what? Alpha times T of X. So T of X plus Y is equal to T of X plus T of Y. T of alpha X is equal to alpha into T of X. Homomorphism you have studied in groups as well as in rings. There you will check the homomorphism condition for, in group theory, only for one binary operation, either star. Say there you have studied like phi of, say phi of G1 star G2 is equal to phi of G1 star dash is the operation in G dash. So phi of G star dash phi of G2 you have studied like. In ring theory, so you shown the linearity condition for both operations. The operations are there, one is the addition and the other is the multiplication, they are fixed. So in ring theory you have studied like G of phi of say two elements x1 plus x2 is equal to, say you have shown that phi of x1 plus phi of x2, and phi of x1 into x2 is equal to, x1 into x2 is equal to phi of x1 into phi of x2. Here the operations are addition and scalar multiplication. So we prove the linearity condition, T of X plus Y is equal to T of X plus T of Y, and T of alpha X is equal to alpha into T of X. So now T is a homomorphism. Suppose in addition to that, T from V to W is a homomorphism. Additionally, it is 1 1. 1 1. Then T is said to be what? You have studied this definition. T is a isomorphism. T is a isomorphism. So T is an isomorphism. T is homomorphism plus T is homomorphism plus 1 to 1 condition. T is homomorphism plus 1 to 1. Then we say T is an isomorphism. And we say V and W are isomorphic. The vector space V and W are isomorphic. Written V is isomorphic to W. V is isomorphic to W if there exists an isomorphism of V onto W. Okay. So we say V is isomorphic to W if there exists an isomorphism of V onto W. For example, you can define the map, say identity map I from V to V. The identity map I from V to V such that I of x is equal to what? The identity maps element itself. I of x is equal to x. I from V to V such that I of x is equal to x is definitely an homomorphism, as well as it is 1 1 as well as onto. Therefore, we say this is an isomorphism. Also the zero map. Zero map is 0 from, say this is a zero map from V to V such that 0 of x is equal to what? 0 of x is equal to 0. 0 of x is equal to 0 for every x belongs to V. Then this is also a homomorphism. We can show it. Okay. So identity map as well as the zero map, they are homomorphism, and since they are 1 1 and onto maps, we can say they are the isomorphisms. Another non-trivial, these are the trivial examples. Okay, let's discuss the non-trivial example. Say you take another, say V is R3, V is R3 over R. V is R3 over R. Say W is, say the another vector space is R2 over R. V is R3 over R, W is R2 over R. Define a mapping T from V to W. Define a mapping T from V to W by T of x, y, z. T of x, y, z is equal to x comma y. This is nothing but the projection map, right? T of x, y, z is equal to x comma y. Then we can see that T is an homomorphism of V into W. Then we can say that T is an homomorphism. T is an homomorphism of V into W. So you know what's meant by fundamental theorem of homomorphism of vector spaces. So the fundamental theorem of homomorphism of vector spaces. Fundamental theorem of homomorphism of vector spaces. Suppose V and W are unit to vector spaces. Suppose T is a homomorphism of V onto the vector space W. Suppose T is a homomorphism from the vector space V onto the vector space W with kernel say denoted by K. Then V by K is isomorphic to W. If V and W are into vector spaces, and if T from V to W is a homomorphism from V onto W with kernel K, then V by K is isomorphic to W. Okay, what's kernel means? You know, kernel or the null space. Kernel of T is equal to, that is usually denoted by K or T. So this contains a set of all V belongs to V such that T of V is equal to 0. It contains set of all V belongs to V such that T of V is equal to 0. So means it contains those vectors of V which are mapped onto the 0 element of W. Which are mapped onto the 0 element of W. So this is also known as the null space of T. Null space of T. In fact, we can prove that kernel of T is definitely a subspace of V. Then only we can construct the quotient space. Okay, kernel of T is a subspace of V. Okay, let's look at some example based on this one isomorphism. Say, suppose A and B are any two subspaces of a vector space Vf. Suppose A and B are any two vector space, subspace of vector space Vf, then A plus B by A is definitely isomorphic to B by A intersection B. Okay. So now look here. Now A is a subspace, definitely a subspace of A plus B. Now if A is a subspace of A plus B and A intersection B is a subspace of B, A intersection B is a subspace of V, therefore A is a subspace of A plus B means A plus B by A definitely exists and B by A intersection B exists, because so quotient spaces constructed only using the subspaces, right? So now you define a map T from B to A plus B by A by T of B is equal to what? T of B is equal to A plus B. T of B is equal to A plus B, where B belongs to B. Because how the elements of A plus B by A looks? So A plus B by A looks like, so they are the elements of the type A plus B, where B belongs to S, where B belongs to A plus B. So I will take B belongs to B. So now T is a homomorphism, or it is also called the linearity condition. For this, let B1 and B2 be any two elements of B and alpha comma beta be scalars. Then T of alpha B1 plus beta B2 is equal to, according to our definition, this is like B, A plus alpha B1 plus B beta times B2. So this is equal to A plus alpha B1 plus A plus beta B2. So alpha I can take it outside, alpha into A plus B1, because alpha can be taken out, although alpha is not here means alpha into A is a subspace means what? Alpha into A again is in A only. Alpha into A is again A only, therefore alpha can be taken out, alpha into A plus B1 plus beta into A plus B2. Therefore alpha into A plus B1 is what? T of B1, and A plus B2 is what? T of B2. Therefore alpha into T of B1 plus beta times T of B2. So T of alpha B1 plus beta B2 is alpha times T of B1 plus beta times T of B2. Therefore T is a homomorphism, or T is linear. Now T is onto map. Look here, T is onto. For if you take, say, A plus X is any element of the codomain, any element of the codomain A plus B by A implies, because that this is the codomain. Okay, T is a mapping defined from B to A plus B by A. I will take, so how to show something is onto means we have to take some element in the codomain and we need to show there exists some element in the domain space such that the image of that element is the chosen element. Okay, so for this I chosen the element A plus X belongs to A plus B by A. This implies what? X belongs to A plus B. Okay, this implies X is equal to A plus B, where A is an element of A, B is an element of B. Therefore A plus X is equal to A plus B. So this can be written as A plus A plus A plus B. Since A belongs to A plus A is A itself, A plus B. Now A plus A is 2A plus B, so 2A is again A only. A plus B, that's equal to A plus B means T of B. Thus there exists the element B belongs to B such that T of B is equal to A plus X. T of B is equal to A plus X. Therefore T is onto. So T is a homomorphism, T is onto. Therefore by fundamental theorem of homomorphism of vector space, what you can say, B by kernel of T is isomorphic to A plus B by A. Now what is the kernel of T? Kernel of T contains set of all x belongs to B such that T of x is equal to the 0 element of A plus B by A. What is the 0 element of A plus B by A? Or the null space, 0 element means this is A only, because in the quotient space V by W, what is the 0 element? W itself is the 0 element. So this is equal to set of all x belongs to B such that T of x is what? A plus x is equal to A. This is equal to set of all x belongs to B such that A plus x is equal to A means what? You can say x belongs to A. So this is equal to set of all x such that x belongs to A as well as x belongs to P. So this is x belongs to B. So this is equal to what? A intersection B. Therefore, in place of kernel of T, I can take B by A intersection B is isomorphic to A plus B by A. This is the one example. So that's all for this first class. I'll continue in the next class. Thank you.